Hi, my name is Mukund, and I'm a current senior in high school presenting from Capel, Texas. My Polygence project is on the topic of spin glasses, which is a statistical mechanics phenomenon in which the magnetic spins of particles are aligned randomly. And I chose to work on this research topic because I want to learn more about quantum computing algorithms and how they can be applied to difficult optimization problems like the problem of spin glasses, which I'll discuss more about. Okay, so first I will begin by explaining the background information about the different concepts in this project, since there's a lot of things to unpack. And the first thing I want to start with is what is a spin glass? So in the field of condensed matter physics, the spin glass is a disordered magnetic state, meaning that its magnetic spins are aligned randomly. So in the state, both ferromagnetic and antiferromagnetic forces compete in the state, resulting in frustration and quench disorder. So ferromagnetic forces result from spins that are pointing in the same direction, and antiferromagnetic comes from spins in opposite directions. And physically, spin glasses are represented as magnetic alloys that consist of a host metal and impurities, with less than 10% of the alloy containing the impurity. So some examples would be the copper manganese alloy and the gold iron alloy, with copper and gold as the host and manganese and iron as the impurity in this case. And in the image shown to the right, the top figure represents a spin glass with randomized spins. And the bottom figure is a ferromagnetic state with all the spins pointing upwards. So more about spin glasses. Frustration, which I referred to earlier, represents the unsatisfied bonds that form between spins due to the existence of both ferromagnetic and antiferromagnetic forces, which compete with each other. And quench disorder is a general term that describes the randomness and inherent in the system at all temperatures and energies. And another thing of importance is that spin glasses are related to NP problems, which are optimization problems in the field of computer science, well known for their difficulty. And the image on the right shows a graph of the energy state space of the spin glass, which shows how uh, the spin glass could be trapped in a state that is not the minimum possible due to a barrier that is formed by frustration. So in this case, this valley here would represent a possible place that spin glass could be stuck at and couldn't pass due to the barrier that's here, even though the optimal state would be this lower value here. Okay, so the next thing to consider is the Ising model, which is a model with spins of either positive or -1. And this is classified as an NP hard problem, meaning it can't be solved by classical algorithms efficiently. And so quantum computing can help. And the Edwards-Anderson or EA model is a specific form of the Ising model that describes the interaction between neighboring spins using the mathematical formula shown here. So the capital J in this represents the weighted bond strength between adjacent nodes I and J. And SI here and SJ here represent the individual values of the nodes. And this formula is called the Ising energy Hamiltonian, which represents every possible configuration of the spins. And so this model assumes the principle of nearest neighbor interaction, in which each lattice site only interacts with the sites directly adjacent to it. So in this case, there can't be any diagonal interactions between nodes. They have to be directly adjacent to each other, which generally forms squares and square-like lattices. So next, I'll take a look at the method used to solve this problem, which involves the use of quantum computing. So first up is the max cut problem, which is an NP hard problem in which you have to find the cut that will lead to the greatest number of edges between each set of nodes. So in the image here, the max cut divides the nodes into a set of white and black nodes. And the edges highlighted in red here signify an edge between opposite colored nodes. So in this case, the max number of edges would be 1, 2, 3, 4, 5, all the highlighted red edges. And for a graph with 5 nodes, there will be 2 to the 5 or 32 different combinations of cuts from which the best must be found. So this problem scales exponentially as the number of nodes increases. And the problem of spin glasses can be transformed into a max cut problem by converting it into a graph like this and approximating it with QAOA, which is what I'll discuss next. So the quantum approximate optimization algorithm, or QAOA, is a mix of quantum and classical algorithms to solve optimization problems. It follows the rule of the adiabatic theorem, or adiabatic quantum computation, which describes how a standard energy Hamiltonian that starts in the ground state can be transformed into the ground state of the desired Hamiltonian by evolving it very slowly. And this quantum algorithm provides an approximation to the problem, but not an exact value. And so it provides a significant speed up over other classical algorithms used. So more about the QAOA algorithm. The QAOA starts by choosing random angle parameters known as gamma and beta, which is then given to a quantum circuit. And this circuit returns an output that is fed to a classical optimizer, which will calculate the cost of the potential solution and tweak the angle parameters as necessary. And then it gives it back to the quantum circuit to run again. And so basically, it's like a cyclical algorithm that runs again and again. And this process is repeated until the optimizer has reached the optimal solution. So now that I've discussed all of these different concepts, we can put them together to solve the problem. So the step-by-step process to solving the problem would be first processing the spin glass data as a set of input weights for the QAOA algorithm, and then running the QAOA algorithm on the given weights, and finally interpreting the results to see what the solution would look like on the spin glass lattice. So as I stated earlier, the Ising spin glass would be an n by n lattice with positive or negative 1 values for each spin. So they could be a 2 by 2, 3 by 3, or 4 by 4 square lattice. And the input for QAOA would be the set of weighted bond strengths between each adjacent spin divided by the temperature of the system, which would be the input weights for the QAOA algorithm. So in this scenario, J subscript 0, 1 would be the bond strength between node 0 and node 1, and it would be divided by the temperature of the system, and you'd apply this operation to every single edge between node 1, node 2, node 2, node 3, etc., all the way until all the bond strengths have been covered. And the number of qubits is in this quantum circuit would equal to number of edge weights in the graph. And so the equation that would relate the number of qubits to the number of nodes in the graph would be this equation here, Q equals 3n minus 4 divided by 2. And for the framework I'm using, which is called Qiskit, I'm using a 32 qubit simulator. So if I set the Q here equal to 32 and solve for n, the max would be 22 nodes of a graph that can be solved. And this means that a 4 by 4 lattice, which I mentioned before, would be the highest. So QAOA, I ran it on IBM's Qiskit framework in Python. And the steps that follow the algorithm are first initializing the angle parameters to random values, and then preparing the quantum circuit, which consists of Hadamard gates, which are H gates that are shown here that set the qubit into superposition, position between 0 and 1. And the C0, and the next step would be the C0 and RZ gates, which are 2 qubit gates that link each qubit together with the weight equal to the bond strength between them. So the operator here would, this plus operator, these two plus operators would be the C0 gates linking them, and the RZ operator acts on Q1 in this scenario. And the weight here would represent the bond strength between node 0 and node 1. And at the end, you would apply a RX gate at the end, which is a mixer Hamiltonian that prepares the circuit to be measured. And after running the quantum circuit, this entire circuit here, the measured result is collected as a binary string that can then be processed. And so we come to the final part where the binary string can be interpreted to find the graphical solution. And in the binary string, each node is represented by either a 0 or a 1 in the string, and they're listed in clockwise order from the bottom left. So 0, 1, 2, 3 clockwise like this. And each node that is 0 can be represented with red, for example, and each node that has a value of 1 can be blue to visualize the solution. And this maximum cut here of the Ising spin glass will also lead to its ground energy state that we were trying to find in the beginning. And so with this, we've successfully found the solution much faster than a classical computer could. So although I've described all of the specific steps for implementing the solution, I'm still developing the working prototype of the QAOA, solving the spin glass lattices. So my next immediate step would be to finish that. And after I finish programming the entire algorithm, I'd like to look at how the quantum statistical techniques that I've used in this in my research can be applied to other optimization problems, such as the patient admission scheduling problem, which is a problem within the medical field about the optimal assignment of patients in a hospital to beds that suit their needs, or the traveling salesman problem, which is about finding the optimal route between two locations. So here are the sources I used for my images, and thank you for listening to my presentation. I hope you find it interesting.
Awesome. Thank you so much for that presentation. So I'll open it up again for the attendees. If you have a question, feel free to drop that in the Q&A section at the bottom of your screen. Mukund, I had one question to kind of start off. Can you talk a little bit about what got you interested in spin glass theory? Like I'll be perfectly honest, this is the first time I've ever heard of spin glass theory. Can you talk about sort of like what sparked your interest and kind of what led you to want to research this?
Okay, so when I first went into Polygence, I wanted to learn more about quantum computing algorithms that can be used to solve difficult problems like this one. Initially, I recommended to my mentor to try out some like well-known algorithm like Shor's algorithm for factoring or Grover's algorithm for structured searching, which are like well-known problems within quantum or algorithms within quantum computing. But my mentor recommended me to try something new or different so I could learn more about it. And while I was researching, I found out about spin glasses, which I found to be very intriguing. I've never heard of it before until now, so I feel like that was something completely new that I learned, and I wanted to try it out. It was pretty difficult to learn about since I would say it's a very obscure topic. Not many people know about it unless you're like a statistical physicist who's working in the field. So I feel like that's what makes it really interesting, and I'm sure no one else would have heard of it. Like the people who are listening in too. I feel like it's a very niche topic. Yeah.
And I will say, I'll be the first to say that I'm not a statistical physicist. So it was definitely a new theory for me. I'm curious because from what I understand in your presentation, spin glass theory is just that, it's a theory. Can you talk a little bit more about sort of the practical implications of spin glass theory? Because you touched on it a little bit. I'd like to hear a little bit more just about how this could be applied in a practical situation.
So yeah, I would say spin glass theory is mostly theoretical. I would say the field is still trying to figure out more about spin glasses, like how to implement them, I guess, and more theoretical, I would say, based on the research papers I've looked at. I have seen an interesting application of spin glasses because they're considered to be like chaotic systems. And so I saw an application of spin glasses to world wars that have occurred previously, like related to history, like World War I, and how the different countries that were fighting against each other were considered as different agents, and how you can model them using spin glasses, which was a pretty interesting read. But other than that, I would say it's pretty early to consider any like real practical implementations. This is still a problem that's still being worked on. So I feel like I chose a topic that hasn't been brought out into the spotlight yet, but I'm hoping to learn more about it and potentially try to find a solution that could bring it into importance. Yeah.
Great. I had one more question for you. As far as sort of next steps, are you going to continue to research spin glass theory, or are you sort of kind of leaving it as is and then moving on to a different theory? What are sort of your next steps in terms of exploring this topic?
So actually, I would I would think my next step would be to implement the algorithm that I mentioned here. I've researched all the physics. I researched how to create the quantum circuit. Like I mentioned, like all the quantum gates I would use, and I've actually created the program for it. It's just I'm running into a lot of issues with running the program. I think it's mainly some problems with the Qiskit simulator. I think I've gotten down like the logic and everything of the entire problem, and I would think, because I'm not fully done with my project yet, so I still have like a few more sessions to go. I'm planning in those sessions to complete the problem or complete the program to solve the problem. And once I get those results, I was thinking of actually creating a research like paper on this issue, because I did a lot more research like on the physics part rather than like the programming, I would say. So I feel like it would be good to create a research paper based on all my findings and all the information that I've gathered. I feel like this is a pretty it's not well known, and I want to like publish a research paper that would like show it more or showcase it more. Yeah.
That's great. I actually had one last question about the fact that this is sort of a niche topic. Did you run into any challenges with resources, sort of the existing literature that was out there?
Yeah, I definitely did. So like the research papers that have already been in there, honestly, they were a bit too complex for me to understand. I could understand like bits and pieces here and there, but I came from like a programming background, not a physics.
Mm.
So it was really difficult to understand the concepts. I was able to find a good website that like explained it through the programmer's view instead of the physicist's point of view, and how to implement it using quantum computing. So that was really helpful for me. That's why I'm still running into issues, honestly. It's because there isn't really a clear-cut path onto how to like solve the problem. So I'm just trying to like put bits and pieces together, someone solving a specific version of this problem and trying to apply it to my own specific version. So I would say the difficulty for me is in applying whatever I've found online to my specific situation. Yeah.
Great, great. Fantastic work. Really, really interesting topic. Well done.
Thank you. Yeah.